Okay. So we now know the 4 important variables that can be used to completely describe a sample of gas. These variables can also be used to completely describe other states of matter, but we're predominantly going to be, well, we're solely going to be looking at gases in this unit. And that's volume, pressure, temperature, and the number of moles. And for the next 2 or 3 days, we want to look at relationships between these differing variables. The first one we want to look at today is how are pressure and volume related? If I change the volume of a gas, if I can force the volume of a gas to be larger or smaller, maybe by squeezing it into this syringe, what happens to the pressure? So we want to look at the pressure-volume relationship. Tomorrow we're going to want to look at the volume-temperature relationship. What happens to the volume of a gas if we change the temperature? All right? So we're going to go through all these different relationships so that we have a good understanding of the way gases behave, which means we're going to have to take some data and we're going to have to graph that data in order to figure out their mathematical relationships. Now, this is more like physics than it is chemistry. Really, it is. We're not talking about chemical reactions. We're not talking about mole ratios or balanced chemical equations. We're talking about the physical relationship between 2 variables, pressure and volume of a gas. And that's what physicists do. They do experiments, they get numbers, they make a graph, and they see if they can come up with a conclusion about the way that behaves. So before we can get some pressure and volume data, which we will get at the end of the class, I want to talk a little bit about some relationships that we are going to encounter in this class. Now, the first possible relationship that we're going to deal with is a direct relationship. For all direct relationships, as one variable increases, the other variable increases. Now, I'm not a fan of the second bullet here, a line passing through the point 0, 0. That's if we're not talking about a partial linear relationship. And if you remember your math, you would have done all that good stuff. All I'm worried about is the example of the direct relationship that I'm going to be dealing with. So I'm going to put here A. We're going to be looking at a linear direct relationship. So the example we're going to be working with is a linear relationship. And this is as simple as the math gets. We're really taking a step back in your mathematics, but I want to now put it in the context of an experiment. So we're going to get some data, and we're going to plot it, x versus y. We're going to make a graph, and if we've got a nice straight line, we can then say that y is directly proportional to x. That's the statement we make. When we have a nice straight line, we can say that y is directly proportional to x, and we represent it with this little symbol right here that might look like an A, but it's actually a Greek letter. It's an alpha, and if you draw it, maybe elongated, it looks a little bit like a fish. And that's the symbol that we use that essentially says is directly proportional to. So if we get a straight line, we can make the statement, y is directly proportional to x. This is really basic linear mathematical analysis. Now, we know that the equation for a line, well, again, good old math, they know how to indoctrinate, I tell you, but I'm getting there with my molar math, but I'm not there yet. Equation of a line. Oh, that's fabulous. You guys are great math zombies. Y equals mx plus b. All right? Really, it's truly indoctrination. It's like you guys are in church and you're spouting out some kind of a prayer. Y equals mx plus b. It's exciting. Anyway, in our graphs that we're going to encounter, they will always run through 0, and therefore, what can I say about this equation? If they all run through 0, yeah, I can get rid of the b, and I can just say y equals mx. All right? Math likes to use m that represents, what does the m represent? The slope. Science, for some reason, we like to use k as a constant. It's just something that in many scientific things that you have k as the constant. So I'm going to write the equation as y is equal to some constant k times x, where I've simply switched m for k. I don't know why. That's the way every time we go through this, from a science perspective, we always put k. All right? So if we have a straight line, we can make the statement y is directly proportional to x. We can shorten that up with this nice little symbol, y is directly proportional to x. And we can make an equation, y is then equal to some constant times x. All right? And that constant there is still indeed the slope. All right? And if we wanted to do some deeper analysis, we could use that, but we're not going to get into that. Grade 12 university physics, you'll do all kinds of neat stuff. That says slope, and I wanted it to point at that k. There it is. That's better. Okay? Now I want to talk to you about something that in science we call the relation equation. I don't know what you call it in math, but in science I call it the relation equation. We can relate 2 points on the line, all right? And we can generate a useful equation from that. We can call the first point, good old math, x1 comma y1. And we can call that second point, good old x2 comma y2. Not right now, Mark. I've got some stuff I've got to do, okay? All right. So each of these points exists on the line, and therefore I can put them into my equation. Y1 is equal to k times x1. And because it's on the same line, I can say that y2 is equal to k times x2. Right? Those are just 2 points that are true for that line. Because they're on the same line, k is the same for both of them. So I could actually put those two equations together through the k. I'm going to divide off the x and bring it down here. So I'm going to have y1 over x1 equals k. All right, everybody okay with that mathematical move there? Let me know if things are moving quickly. I can bring this x down here as well, and I can get y2 is over x2 is also equal to k. All right? And because we're on the same line, the k's are the same, so I can make the statement y1 over x1 equals y2 over x2. All right? And that right there is what we would call the relation equation. Relation equation. Why? Because it relates 2 points on the same line. It means that if I have two variables, at one point I know the information, and I know where I want to go for one of the other variables, I can always solve for that fourth unknown guy. All right, I can always solve for that. I'm going to rearrange this relation equation just to show you one other interesting thing. I want to bring the y's to the same side and the x's to the same side. So I want all y's on one side and all x's on the other side. I'm going to bring this y2 over to the left, and that means it's got to go on the bottom because I've got to divide it off. And I want to bring this x that's on the bottom over to the other side, and that's going to bring it to the top because I've got to multiply it when I bring it to the other side. So that means I'm going to have y1 over y2 is equal to x1 over x2. Now that's also another version of the relation equation. There's nothing wrong with it. I like the way this one is because it keeps all the ones and twos together. But you can see that it's linear and direct as opposed to inverse, because my next equation is going to have an inverse relationship. But you can see that it's a direct relationship because I've got the ones on the top and both of the twos are on the bottom. If it was an inverse relationship, it would be flipped. I'd have one on the top and the other one on the bottom. All right, so that's one type of relationship that we're going to encounter in this particular unit. There are many other types of direct relationships. Don't write this down, but you could have a direct relationship that is squared. That's my rendition of a parabola. We would say for this one that the y is proportional to the square of x. You might encounter that in physics, but we're not going to encounter it here. You could even have one that curves over like this. That's supposed to be a parabola on its side. With that, y is proportional to the root of x. There's many different direct relationships that you can have in science and in math, obviously, but we're only going to encounter linear ones. All right? You can do the same analysis for all of these different equations and get a relation equation for all of them. I used to teach that when I used to teach the grade 12 university physics. Mr. Petrus does it now at the beginning of his, and that prepares you for when you run into different relationships in physics. The next relationship that we possibly can run into is an indirect, and again, there are many indirect relationships, but the specific one we're going to look at is inverse. For all indirect relationships, as one variable increases, the other one decreases. It's indirect. It does the opposite. When you graph an inverse relationship, you get a curve that looks like this. Because as as x gets big, y gets small. And if x is small, y is big. The opposite, the inverse. If you see a curve like this in your data, I want you to say to yourselves, oh, if I get a curve like that, I know that y is inversely proportional to x. And I can say that y is directly proportional to the inverse of x. So it's related to the inverse of x. All right? I can go from this proportional statement to an equation, just like I did on the last slide. I can say that y is equal to some constant divided by x. So I just put a constant in, just like I did before, but now x is on the bottom. Again, I can deal with 2 points, x1, y1, x2, y2. And I can do the same with the equation for this one. Before I put them in, I'm going to move the x. If I have an inverse or indirect relationship, then in this case, I'm going to have y times x equals k, because I brought the y up to the x to the other side. Now I can say y1 times x1 equals k, and I can say y2 times x2 is also equal to the same k. Because they're on the same curve, the k is the same, and therefore we can say that y1 times x1 equals y2 times x2. And that is the relation equation for an inverse relationship. Relation equation for inverse. All right? I just want to rearrange this inverse one around just so that we can compare it to the last one. I want all the y's on one side and all the x's on the other side. So I'm going to bring this y2 down to the bottom. Y1 over y2 equals, because I brought the y2 down here. And I'm going to bring this x1 down over here. That means I've got x2 over x1. And when you put it in this form, you can see that it has to be inverse because I've got 1 on top of the one side and 2 on the other side. In other words, it's like something's been flipped. It's inverse. Okay? All right? Now looking at the time, I'm going to jump through a couple of steps and then I'm going to amend our little activity that you're going to do for homework. It turns out that all inverse relationships kind of look the same. Don't write this down, but if I had a situation where y was proportional to the inverse of the square of x, it'd look the same. And if I had a relationship where y was proportional to the inverse of the cube of x, it also looked very similar. So it's hard to tell which inverse you've got. The way you fix that is you make a graph of 1 over x. In other words, you take all of your numbers in the x column and you calculate 1 over x. You actually do the inverse of the number. And if you do that, and you now graph the inverse of x with y, it will give you a new straight line. And that's what we call curve straightening. You'll do that in physics. I'm not going to worry about it right here for today. Now we're going to do a little activity here. Boyles' law. Don't write this down. I have it all on a page. Boyles' law is the relationship between the pressure and the volume of a certain amount of gas that's caught in a reservoir, like in a tube like this. And we're going to take some quick data here so that you can graph it and determine what that relationship is. So here's a page that has that definition on it, along with a grid so that you can take some data and instructions on how you're going to analyze the data. I'm also going to give you a piece of graph paper in a moment when we're done taking the data. So we want to look at the relationship. Are we short one? We want to look at the relationship between pressure and volume. And if we're going to look at the relationship between pressure and volume, we need the other factors to remain constant. Temperature is going to remain constant, and the number of moles or the amount of gas is going to remain constant. I normally do this experiment with an apparatus like this. I can take the syringe, which is connected to this meter with a hose, and I can remove that hose, and I can pull out the plunger, and I can trap some air in that space. I can reconnect it to the meter, and then I can start making the volume smaller, and you can see the pressure changes. This is a real apparatus, and it works very well. Because I'm making a recording, I want to show the people who have to watch it what it looks like here. So I've got a simulation running that is the same as this. All right? It's exactly the same. So I'm going to run this on the simulation. Okay? You're going to take data of pressure and volume on your chart. Okay? We're not going to do the calculation 1 over pressure, so you can ignore that column. Just don't bother with it. All right? So here's the real apparatus. It works very well. This is the artificial apparatus. It's going to work just fine. If you take a look, we've exposed this to the air, just like this. This is now reading the pressure of the atmosphere, and take a look at what the number is. What's the number reading on that?
6. No, sorry.
That's okay. It takes a minute to figure it out. So this is 5, 10.
You have like 14.
It's about 14. It's really close to 14.7. What unit measures the atmosphere at 14.7? PSI. So you can see here, we're reading PSI. The first number I'm going to give you is 30 milliliters. So I'm just going to click on it. Click. Now take a look. It reads 35 milliliters, and that's because there's a little bit of air in the tube as well. So your first data point, 35 milliliters, is 14.70. Okay? 35 milliliters is 14.70. All right? Now I'm going to push this into about what is reads as 25, and I'm going to let it go. And this is reading 29.68 milliliters is 17.33 psi. Now you might think, oh, this is a simulation. This isn't real science. And I would agree. This simulation only works as well as the computer program made it, right? The programmer did. But we could have done it with that real apparatus. It does work, all right? I'm going to move this to 20. They seem to be all a little higher by 5. And so I've got 24.83, and the pressure is 20.72 psi. I'm going to move this to 15, and that says 19.72 is 26.09 psi. And we'll do a few more data points. I'm going to move that down to 10. .71 milliliters, 34.98 psi. And let's do one more down at the 5, and well, look at that. The nice thing about a simulation is if I did this on the actual experiment, it wouldn't function, and I'll talk about why in a moment if we've got time. But this, I can still get that reading. At 9.71, we have a pressure of 52.99. Okay? Now, in a moment, I'm going to hand out a piece of graph paper. And your assignment, because I am going to want this handed in, I want to see you do a little bit of graphical analysis. Your assignment is to make a graph of volume versus pressure, all right? It tells you which axis to put the pressure and the volume on, okay? Make your graph take up like 2/3 of the page, all right? And you're going to look at the line or curve. And you're going to tell me whether you've got a linear or an inverse relationship. And in the end, you're going to eventually tell me what the relation equation is. Okay? Now, in my note, I have x's and y's, but on your graph, you're going to have p's and v's. So when you write your relationship and your little symbols, put it in terms of p's and v's. So you'll have P1s and V1s instead of X1s and Y1s, okay? When you're making your graph, don't forget to put appropriate titles. For physics, pressure versus volume graph is enough. Don't forget to put your appropriate units, right, on your axes, all right? And don't forget to label things correctly in terms of the axes, okay? So I do want this done for tomorrow. It won't take you long. So if you're answering the questions, you're doing number 1. You're not doing number 2 because we're not going to do that little inverse part of it. So you're not doing any part of number 2, and you're doing number 3. You're telling me the relationship, and you're giving me the relation equation, okay? In terms of P's and V's, not in terms of X's and Y's, all right? So I'm going to hand out the graph paper in a moment. I'm just going to get this thing to stop for a second here.